Good day. I'm going to solve the following physics problem. So let me read it first. And welcome to the Physics Exercises channel. So you have a chain of length capital L and a total mass m. And the chain is released from rest with its lower end touching the top of the table, as in figure part A. Okay, so in other words, this part of the figure here. Okay, so that's where your chain is. Okay, and it's length L. Okay, you release it, and it starts to fall on the table. And you want to find the force exerted by the table on the chain after it has fallen through a distance x. So here you have L minus x, okay, and x is on the table. Okay, now to solve this problem, the first thing I will introduce is what I call, or what is called, it's not only me who calls it that, is the linear mass density. Okay, and I'm going to call it lambda. And we're talking about a chain which is a homogeneous object, and its linear mass density is mass divided by the length of the chain, the total mass divided by total length. Okay, and from this linear mass density, we can easily solve the first part of the problem, because the first part of the problem is how much force must the table exert to sustain this chain. So that's actually a normal force, you might say. And the mass associated with that part, let me call that small m, I'll call it small m prime, is lambda times x, or in other words, m over Lx. And the force, F1, has to be mLx times g. But that's not the full solution of the problem. That's only part of the solution. We need an F2 because as the chain falls, the table has to stop the chain. Okay, and to solve that, we're going to assume that the chain consists of infinitesimal little masses. Okay, so for example, at this particular height, okay, so let's say I have a height here, and at this particular height, which I don't know, I might call y, actually it's L minus x, but whatever. There's a tiny mass of dm, okay, which is going to fall this height y before it hits the table. And while it's falling through this height y, it's accelerating thanks to gravity. Okay. So the first thing we have to do is we have to calculate the speed of this dm, okay, which is at a particular height. Actually, I really can't call that height x. Okay, so I'm going to because when the chain is in this position, in this configuration where x, the length x is on the table and L minus x is still falling, then actually you are stopping the part of the chain which at the start was at a height x. Okay, so here's this part which is at a height x. When the chain is released, it's going to fall through a length x, or a height x, you might say. So actually you can say that its gravitational potential energy at the start is dm times g times x, which also means that when it falls down to the ground at this point, right before it hits the table, it's going to have a kinetic energy of dm over 2v squared. Okay, dm over 2v squared. Okay, so from this information, we can say that, well, we can, for example, calculate v. So v is actually square root of 2 times g times x. Okay, so the part of the chain that's falling when the chain is in this configuration has a velocity, that little piece with mass dm has a velocity given by 2gx, okay, square root of 2gx, which means that its momentum just before it hits the table is also dm times square root of 2gx, but we actually see that this is an infinitesimal momentum. Okay, yeah. And now what we want to do actually is to calculate a force. And how do we calculate a force? Well, to calculate a force, actually, to turn this into a force, we have to divide it by an infinitesimal time. Okay, we divide it by an infinitesimal time. Why? Because this object falls through a distance x, okay, and then its momentum is re-zeroed, or is zeroed, okay? Well, you might say re-zeroed because it's zero also initially here. And it's re-zeroed in an infinitesimal time, okay? So this is actually going to be the expression of the force, okay? But now, what we need is to can get a close expression by using the linear mass density, because our linear mass density is lambda times dy. Okay, the actual mass of this tiny chunk of the chain, which I've been calling dm until now, can be written as lambda times dy. Okay, dy is an infinitesimal length in this direction. And now when I put this all together, it's going to be lambda dy dt square root of 2gx. But watch what happens. Dy dt is, of course, the velocity of the object when it hits the table, which you already calculated. Okay, so I'm not, it's the notation here is different, but that's what one has to realize, that this dy dt is none other than the velocity of that chain link as you hit the table. So what you're going to have in the end is lambda 2gx, or if you substitute for lambda, it's going to be m over L. Let me put the 2 out here, gx. And here was our first force. This is our second force. Let me now label this as 2. And the total force is going to be 3 mgx divided by L. Okay, so that's the full solution. Is there anything else that I have to solve for? No. Okay, so this is the solution. Okay, thank you very much and have a nice day.